Hey everyone, and welcome to This Explainer. Today, we're diving into something completely fascinating, a topic we're calling the other receptor, serotonin 5-HT2C, and the psychedelic balance. You know, whenever we talk about psychedelics, we usually hear the exact same story. It's almost always told through the lens of a single molecule's lock, that famous master switch that opens the visionary door. But, well, the brain doesn't really work in single switches. Serotonin's signal isn't just one note, it's an entire chord. So today, we're going to look right past the obvious and examine a receptor that just sits quietly in the background. It restrains dopamine, it tunes our mood, and it actively resists the very effects its sibling unleashes. Think about it. What if the key to the psychedelic experience isn't just the receptor that opens the door, but the hidden variable in the shadows that's holding it back?
All right, part one, the master switch versus the shadow.
To really understand what a trip actually is, we have to zoom out and look at the broader serotonin 2 family of receptors, specifically 2A, 2B, and 2C. These three receptors share the exact same chemical language. They use the same signaling pathways inside the cell, but here's the catch. They speak completely different molecular sentences. Take 5-HT2A, for example. We know this one. This is the master switch of the visionary state. It's packed densely in the cortex, opening our perception outward. But then, there's 5-HT2C. Now, structurally, they are twins. They're so alike that drugs actually have a really hard time telling them apart. But in the brain, location is destiny. Because the 2C receptor is scattered deep throughout the limbic system, the basal ganglia, and the hypothalamus, it sits right at the crossroads of mood, motivation, and reward. And this isn't just a fun fact about brain geography. This specific location actively dictates your actual mood and daily drive. So, while 2A opens your experience outward, its near twin, 2C, is just quietly managing the machinery of wanting and reward deep within.
Moving right along to part two, a receptor that edits itself.
Okay, listen to this, because this receptor has an absolutely incredible superpower. It literally edits its own genetic message. Seriously, it completely reframes how we understand the brain, taking it from a piece of fixed hardwired machinery to a living editable text. And it does something that no other known neurotransmitter receptor can do. After the 2C gene is transcribed into messenger RNA, but right before the protein is actually built, a cellular enzyme just swoops in and chemically rewrites specific letters of that RNA transcript. It converts these adenosine bases into inosine. And because this editing process can happen at multiple different sites and in various combinations, the cell can produce a whole set of different receptor variants from just one single gene. It's mind-blowing. The crucial takeaway here is that these newly edited forms differ in how strongly they signal. So this self-editing acts as a literal molecular volume knob. The cell can essentially just reach out and turn the dial to adjust its own sensitivity to serotonin. And we're not just talking about a quirky biological party trick here. This molecular dial is deeply tied to human mood itself, like why you might feel highly motivated one day and totally despondent the next. In fact, altered patterns in this exact editing process have been reported in models of depression and, tragically, they've been linked to the brains of individuals who have died by suicide. It is that foundational.
Which brings us to part three, the brake on dopamine.
So let's uncover this receptor's second superpower, acting as a natural, constant brake on the brain's dopamine reward pathways. If the 2A receptor acts as the gas pedal of cortical excitation, 2C is fundamentally the brake. And to explain this, we need to talk about a really fascinating concept called constitutive activity. Basically, this means the 5-HTC receptor exerts a steady, humming baseline of restraint on dopamine in our reward pathways, even when there is absolutely zero serotonin around to trigger it. It just sits there, all by itself, keeping a firm, steady grip on the dopamine neurons that drive our motivation circuits.
You can think of it kind of like a seesaw. If you activate 5-HT2C, dopamine release falls and your appetite actually drops. But if you block it, dopamine shoots up. This constant daily push and pull on dopamine dictates our most basic drives, our cravings, and our energy levels. It really makes this receptor a quiet, essential workhorse in all kinds of psychiatric, obesity, and addiction research.
All right, let's get into part four, balancing the visionary trip.
So what actually happens when a pretty clumsy key like a classic, non-selective psychedelic such as LSD or psilocin enters the brain and just grips both of these twin receptors at exactly the same time? Well, neuroscientists study this using something called the rodent head twitch response. It's exactly what it sounds like, a rapid movement that acts as a really reliable behavioral stand-in for the psychedelic effect in humans. What they found is that while 2A clearly drives the psychedelic response, basically slamming on the accelerator, the 2C receptor actively pushes back. It rests a calming hand on the wheel to dampen and counterbalance that twitch. So they're literally pushing in partly opposing directions at the exact same time.
What this means is that this super clean, simplistic idea of one drug, one receptor, one effect completely dissolves. The reality of receptor pharmacology is, quite frankly, gloriously messy. Receptors exhibit this thing called functional selectivity, which just means the receptor isn't a simple on or off light switch. A psychedelic might trigger one highly specific chemical pathway inside the cell while leaving another pathway totally untouched. So a drug's overall effect, it's actually a highly complex, delicate balance struck across an entire receptor family.
Let's look ahead to Part 5, Future Medicines and Cautions.
This delicate balance we've been talking about, it isn't just a biological curiosity, it's a vital design lever for future medicines. By precisely turning the knobs on this 2A versus 2C balance, researchers are hoping to design incredible next-generation compounds. Think about things like non-hallucinogenic psychoplastogens, drugs that aim to deliver the profound healing benefits of neuroplasticity without the intense, sometimes terrifying, hallucinogenic trip. Imagine a DJ at a mixing board. The specific ratio of how a drug pulls on the 2A accelerator versus the 2C brake could literally dictate whether an experience feels highly activating, intensely anxious, or smoothly euphoric. But of course, manipulating this system comes with some very serious real-world cautions. Take the cautionary tale of the anti-obesity drug lorcaserin. This drug was designed to specifically stimulate the 2C receptor to lower appetite. And it worked. It was successfully approved. But in 2020, it was abruptly withdrawn from the market after a long-term trial suggested a possible increased cancer risk. It's a pretty stark reminder, proving that manipulating a receptor woven so deeply into our basic survival and reward systems is rarely a clean or simple fix.
And we really do have to ground our enthusiasm in the facts here. While the core neuroscience regarding this receptor's existence, its wild RNA editing, and its dopamine restraint is rock solid, a lot of the deeply detailed work relies on preclinical rodent and cell models. The precise human implications of these self-edited variants are still a very open, rapidly evolving question. And, it goes without saying, but psychedelics remain controlled substances that are absolutely not safe for everyone. As always, everything in this explainer is strictly for educational purposes, not medical advice.
So, to wrap this all together, to truly understand the visionary state is to realize that it relies on this intricate symphony of chemical balances. It's an entire chord being struck in the brain, with 5-HT2C serving as the steadying, restraining note that pushes back against the very effect its sibling unleashes. Once you notice this shadow receptor, you start to see the trip more truly. It's not a simple switch flipped in the dark. It's a fluid, dynamic balance, held and negotiated moment to moment.
As you digest everything we've covered in this explainer, I want to leave you with one final thought. Consider what this self-editing, dopamine-breaking receptor truly tells us about ourselves. If our brain's chemistry isn't just fixed hardware, but a living, editable text actively adjusting the volume of our reality, how fluid is human consciousness, really? It's a massive, awe-inspiring question, but honestly, it's exactly the kind of mystery that makes exploring the brain so incredibly fascinating. Keep questioning and keep learning.